I'm Prof L and welcome to Chemistry Matters. And today we're going to talk about solubility and using the solubility product to predict whether or not we're going to get a precipitate when we mix two solutions. Okay, so in the previous video on solubility, we defined a thing called the solubility product, okay, KSP. And that was to do with the equilibrium for a sparingly soluble salt. So, for example, lead bromide, sparingly soluble, that is an equilibrium if we put it into water with its aqueous ions, lead 2 plus aqueous and 2Br- aqueous, okay? And that's an equilibrium process, so therefore we can write a KSP for that, an equilibrium constant being lead 2 plus concentration multiplied by Br minus concentration squared. Right, so how do we then use this value of KSP in a predicative sense, I guess, is the next question, okay? So KSP for this is equal to 2.1 times 10 to the power of minus 6. We're talking about a sparingly soluble salt here of lead bromide. Now, what we learned in the videos on equilibrium is if we can write an equilibrium constant, we can also write a reaction quotient, Q. So we can also write a QSP. Now, instead of calling that a reaction quotient, it's usual in this part of chemistry to call this an ionic product. And the reason it's called an ionic product is hopefully obvious. It's merely the product of the ions, the product of the concentration of the ions. Lead concentration times bromide ion concentration squared. Now remember, the difference between Q and K is that K, we should really have little equilibrium signs there, and K only has one value at a particular temperature. Q can have any value. But the importance of Q is that we can compare our value of Q with our value of K, and that'll tell us whether we're at equilibrium or not, and if we're not, which way we've got to go to get to equilibrium. Okay, now you've seen that concept before, so let's now utilize that in terms of solubility. And let's say, right, we've got 50.0 mils, excuse me, of 0.01 mole per litre lead nitrate, okay, PbNO3(2), and we have got 50.0 mils of 0.01 mole per litre KbR solution, okay? So both of those salts are very soluble. We can make up these concentrations. They are both fully soluble, clear, colourless solutions. When we mix them, do we then get a precipitate of lead bromide? That's the question. So, in other words, PbBr₂ precipitates, question mark. So how do we then go about figuring this out? What we're going to have to do is we need to evaluate the value of QSP under these conditions and compare it with our value of KSP, and remember KSP in this case is 2.1 times 10 to the power of negative 6. Okay, so again it turns into another stoichiometry problem essentially. What we need to know are the number of moles of lead, number of moles of bromide, essentially then their concentrations, and then calculate Q. So let's go ahead and do that. So the number of moles of lead is going to be conc times volume, and that is going to be 0.01 mole per litre multiplied by 0.050 litres, and that is going to give you 5.00 times 10 to the minus 4 moles of lead. Okay. Then the concentration of lead in the solution when we've mixed our 50 mils and our 50 mils, the The final volume then is going to be 100 mils, 0.1 of a litre. So therefore the concentration of lead is going to be 5.00 times 10 to the minus 4 mole over 50 and 50 is 100, 0.100 litres, and that then is going to be 5.00 times 10 to the power of minus, excuse me, minus 3 mole per litre. Okay, so that's going to be our lead concentration in the solution after we've mixed them, these two solutions. So now we do the same thing for bromide. The number of moles of bromide, again, is going to be concentration times volume, and surprise, surprise, 0.0100 mole per litre multiplied by 0.050 litres, and again, same number of moles. And again, surprise, surprise, the concentration of bromide, Br minus, is going to be this number of moles over 100 mils, 0.1 litres, so 5.00 times 10 to the minus 4 mole over 0.100 litres, and that's 5.00 times 10 to the minus 3 mole per litre. Okay, so essentially what we have worked out now is the concentration of lead in the solution when we have mixed these two solutions, okay, and also the concentration of bromide in the solution after we've mixed those two solutions, okay, and they're both 5 by 10 to the minus 3 mole per litre. So where now do we go with this? Well, knowing those two concentrations now allows us to determine our value of QSP, because QSP is equal to the lead concentration, lead 2 plus concentration, multiplied now by the bromide concentration squared. Okay, there's your lead concentration, there's your bromide concentration, so that equals 5.00 times 10 to the minus 3, multiplied by 5.00 times 10 to the minus 3 squared, okay? And if you do that calculation, you get 1.25 times 10 to the power of minus 7, okay? 1.25 times 10 to the minus 7. That is your value of Q. Here is your value of K. So what can we then determine from comparing the values of Q and K? We know that Q is less than K, okay? And if Q is less than K, that means that we are certainly not at equilibrium, and in fact what it means is that we're not going to get a precipitate, okay? We're not going to get a precipitate in this case. If Q is less than K, then to get to equilibrium, we've got to go in the right-hand direction towards the ions, okay? Remember, that's what that always means. If Q is less than K, we've got to make Q bigger. The way to make Q bigger is to increase the concentration of the ions, not to precipitate the solid. So in this particular case, when we mix these two solutions, even though lead bromide is a sparingly soluble or a slightly soluble salt, when you mix those two solutions having those particular concentrations, you in fact won't see any precipitate coming out of the solution, because you've done all the stoichiometric calculations. You've shown then that Q is going to be less than K, and so therefore you don't get a precipitate. Now in similar calculations like this, if you get a situation where Q is greater than K, then you've got to make Q less. And the way to make Q less is to go back towards the left-hand side, and that's where you start getting a precipitate being formed, okay? So in a situation with Q equal to K, you'll have a precipitate. In a situation where Q is greater than K, you'll get a precipitate. In a situation where Q is less than K, you won't get a precipitate. Okay, so there you go, the predicative power of KSP and comparing it with the value of QSP, just like we've done in other videos where you compare the values of Q and K to see if you're at equilibrium or not. Okay, so that's it from me for today, and we'll see you in the next video.